Okay, so this is a question. 4 charges, each of magnitude minus q, are placed at the corners of a square. You can see the square here. At the corners we'll have 4 charges. Find the magnitude and sign of the fourth charge placed at the center. So the question is saying that there is a fourth charge at the center. Let us call this q dash. And we have to find out the magnitude and sign of q dash so that the system is in equilibrium. System being in equilibrium means all 5 charges must be in equilibrium. So let's talk about case 1. If q dash is negative. What happens when q dash is negative? The q dash will experience a repulsive force from all the charges This is the repulsive force due to A, this is the repulsive force due to B, this is the repulsive force due to D obviously, and this is the repulsive force due to C. Now since all charges are equal and all distances are equal, magnitude wise we can say FA equals to FB equals to FC equals to FD, and all these forces will cancel out in pairs. Like FB will cancel out with FD and FA will cancel out with FC. Hence, we will have net force equals to 0. Now let's consider another case. Case 2. Q dash is positive. What if Q dash is positive? Let me draw the square again. So here we have A, B, C and D. And there is minus Q here and minus Q and minus Q and minus Q, and here we have Q dash. Now if Q dash is positive, it is not difficult to understand that the forces will be attractive, but these attractive forces will again cancel out in pairs. The force from A will cancel out with C and B will cancel out with D. Hence net force is still equals to 0. So irrespective of the sign of Q dash, net force equals to 0 on Q dash. Now please take care, this is very important. The net force is 0 on Q dash, and we have only discussed Q dash for now. Now if you want to discuss other charges, like the charges placed at the corner, we will have to change page and understand the situation. So this is a square, and again you have 4 charges A, B, C and D. Now and of course there is Q dash. Now again let's consider case 1. Q dash is negative. Now what if Q dash is negative? So let's try to understand this. Now we are not considering force on Q dash, we will consider force on A. So what is the force on A? Due to B, there will be a repulsive force because both are negative. Due to D also, there will be a repulsive force because both are negative. Due to C also, there will be a repulsive force, both are negative. And due to Q dash, the force will also be repulsive because it is negative. So all forces are repulsive in nature. Now please consider this arrangement here. This arrangement is very important here. We need to understand, we need to find out if the net force on charge A can be equals to 0. So let me draw A again, and this is force due to B, this is force due to D, this is force due to C, and in the red line is force due to Q dash, the center charge. Now let's consider first these two charges, force due to B and D, force due to B and D. And we know that force due to B is equals to force due to D because the distances are same and the magnitudes are same. Hence, what will be the net force on this charge? The net force, the B and D will sum out in this direction. Due to C, it is already in this direction, and due to the center charge, it is already in this direction. So we can say that all forces have same directions. Hence, net force on A is not equals to 0. Hence, A is not in equilibrium. Now please try to remember what was the first condition. The first condition was that A should be in equilibrium. That was the first condition. And B should be in equilibrium, and C should be in equilibrium, and D should be in equilibrium, and Q dash should be in equilibrium. The entire system must be in equilibrium. And this is not happening here. This is not happening. So we need to change the polarity of the charge Q dash. And we will move on to case 2. We'll draw another square like this. So that is case 2. Q dash is positive. Now this is A, this is B, this is C, this is D, and you must remember that A is minus Q, B is also minus Q, C is okay. So I have changed C and D. This is D and this is C. So this is also minus Q and this is also minus Q, and this is here Q dash. Now let's consider the forces on A again. Force on A due to B, repulsive, obviously. Force on A due to D, repulsive, obviously. Force on A due to C, you can check, negative and negative, repulsive, obviously. Force on A due to Q dash. Now Q dash is positive, so this force is going to be attractive. This green force is force on A due to Q dash. Now let's have a discussion on the equilibrium of A. This is point A, and these are the three forces, the first two, and these two will be equal. Why they will be equal? Please try to understand. This distance and this distance are equal, the charges are equal, and hence these two forces will also be equal. So they have a resultant, they will have a resultant in this direction. So if we can find out the resultant will be in this direction. The force due to C is already in this direction. Force on A due to Q dash. Now as you can see that this force has the capacity to cancel out the sum of these two forces, and there is a possibility that net force is 0. So in order to sustain that possibility, we have to assume that Q dash is positive in sign. Now what about the magnitude? So let's find out the magnitudes that we already know. What are the magnitudes that we already know? We know the magnitude of this force, KQ squared upon A squared A is obviously the distance. This magnitude is kq squared upon a squared. Again, a is the distance. This force is kq squared upon 2a squared. And why is that 2a squared? Because you will notice the distance between the two diagonals. The distance between the two diagonals, is root 2a. So if you square root 2a, you will get 2a square. So let me draw the diagrams. This is kq square upon a square. This is kq square upon a square. And the third one is kq square upon 2a squared. What do we do first? We find out the resultant of these two. And when we find out the resultant of these two, you will notice that the forces are at 90 degrees. So if they are at 90 degrees and equal in magnitude, if you might remember, just short revision, if there is a vector r and there is a vector r and they are at 90 degrees, so the resultant will be r root 2, if you remember it from vectors. So the resultant of these two forces will be root 2 kq squared upon a squared, and the second force due to the diagonal charge C is kq squared upon 2a squared, and they are in the same direction. So we can move on to next page. So we have two forces in this direction, root 2 kq squared upon a squared plus kq squared upon 2a squared, and then we have the force due to q dash in this direction, and the force due to q dash will be what? The force due to q dash will be what? This is A, this is q dash, this is attractive force, and this distance is a by root 2. So this force is going to be what? F is equals to k q dash q upon a square by 2. So 2 goes up. Now you're going to equate the red force with the white force, or you can say the red line force with the white line force, and you can solve for q dash. I'll just write down the equation. Root 2 kq squared upon a squared plus kq squared upon 2a squared is equals to 2kq dash q upon a squared. You can notice that a squared is out of the scene, 1k and 1q is out of the scene, so you will have root 2, let me write down the equation here, root 2q plus q by 2 is equals to 2q dash, and hence you can find out the value of q dash, and you have to remember that the sign is positive.